Tom Herring is going to give an update on the transition of the IGS Analysis Center coordinator from GI and MIT to NASA, and on the development of multi-GNSS operational products.
Okay, thank you very much. So welcome everyone. So this talk was prepared by Taylor Yates at NASA, CDDIS, who's taking over the role of the combination of all of the products that come out of the final IGS rapid products, ultra rapid products. Has significant contributions from Geosciences Australia in MIT, and we also are working very closely with NRCan, the National Timing Lab, and GFZ. And so we're going to give you an update on the timescale of what's happening in this particular update. Hang on. Oh, okay, so the operational leads here, as I said, are Taylor Yates, Salim Masuri from Geosciences Australia, and then also contributions from Rivers Lamb, Joshua Truman, and myself. So this transition has been happening every 4 to 8 years. There is a change in the group that is actually making all of the final products. And when Geosciences Australia took this over a decade ago, they moved all of the software from individual server systems running at different locations into a cloud environment. And that cloud environment now has been transitioned over to the work at NASA. And in addition to transitioning the legacy software, also there's the development of multi-GNSS capability, and we'll talk briefly about that today. So this new ACC team was to do the transition across and also make progress towards multi-GNSS operations, and also to have the long-term evolution of the ACC be such that it can move relatively easily between other groups later on, in particular in this cloud environment. That's the whole idea, hopefully simple switch of the cloud permanent. So I'm going to talk about the transition to the operations at NASA. And one of the major things that happened that Taylor's worked considerably on has been improvements to that legacy software. So the legacy software goes all the way back to the beginning of the IGS itself. There is still 60,000 lines of Fortran code that are actually used in this. That has not changed. But what has changed significantly is how the operational system interacts with that code. And so if you look at things like the amount of Python scripts being used, that's gone up from 3,000 lines up to 5,000 lines of code. The use of shell scripts, mainly C shell, has dropped considerably. The use of awk has dropped considerably, and the use of Perl has significantly dropped in this code. The figures that you see on the left-hand side is a representation, essentially by color, of how many objects were being used in the original legacy software. And the little red dots are all the crons that happen that automatically control the startup of the operation. On the right-hand side, you can see that as a much less dense system of points, and that's simplified the operations considerably. The other thing which has also been critical here is making sure that the operational system can be easily debugged when something goes wrong. I'm not sure how many of you run codes on a regular basis, but one of the things I always find is that once you actually have an error, trying to work out where that error actually occurred and trying to remember how things actually work is a major problem. So a lot of Taylor's operations, since she comes from a software background, is to simplify all of that out. And in particular, there is a new set of diagnostics running continuously, which are tagged at the millisecond level, which you can see an example of at the below, that allow you to tell the status of where things are, and when things fail, what happens. And there is multiple retries of downloads based on checksums to make sure that the transfer was correct, and then alerts that happen in case things go wrong. So the, oops, did I skip a slide there? Yep, sorry. So the other other change that's happened is all of this software runs under virtual machines, And there is actually a separate virtual machine for the Ultra, the Rapids, and the Finals. And again, the Ultras are every 6 hours. That's very much has to happen on time. The Rapids are every 24 hours. That also has to happen very rapidly. As we saw from the BIPM presentation, that's quite critical. The Finals, which in my mind are the products that we use to do really the long-term stable analysis of the Earth, because we have all the most complete models in the processing of that finals until we go back and do a reprocessing. But those are the highest quality. Those also can run at a little bit more leisurely pace. In fact, those are actually manually checked to make sure they're okay, whereas the other products automatically go out and then problems get detected after they've gone out potentially. So each of those machines runs separately, but each is able to run the other if need be. And this was robustness to make sure that when something fails in this virtual cloud environment, that things do not fall to pieces. There's also a lot of source control, as you can imagine. 60,000 lines of Fortran code alone, that's hard. That's very easy to break. And so there's a lot of source control being put in now and testing environments so that when updates are being made, this is all being done through a Git environment. And it's being put on the NASA cloud environment. This gives us enhanced security. You may have seen concerns of products that we have come in and go out, that they are susceptible to being cyber attacked. And NASA is very aware of that and trying to take it into account. Now, the current operating system is still running at GA. At the end of, it's June now, at the end of this month, it is expected that it will transition and the operational products will be coming from the NASA servers. Right now, we are running the comparison, the big yellow box that you look at, that's the critical one, full of zeros. That's the difference between the system running at GA and the one running at Goddard. Those zeros are actually centimeters, which is not that useful. But when you actually look at them in millimeters, it's down at sub-millimeter differences between the two operational systems. So everyone's very happy with that. The remaining work is we want to validate the automatic clock exchange for the Rapids and the Finals. There is a step in which the timescale gets aligned through NRL. That step is still being configured. One of the problems with a lot of security is that NASA basically doesn't trust the Navy, and so it's so it's hard for the Navy to actually access the NASA machines. They're trying to work out the protocol for doing that. And there's also a lot of automatic emails that are being generated for the ACC at IGS.org. And there's going to be automatic uploads to data centers, et cetera. And the graphics are going to improve. And that's going to be one of the interesting things. I've seen the early versions. So when you're looking at the comparison of how different orbits match, you'll have much more interactive capability with that. Timescale for this is that we started back in July of 2024. The time shift to when it actually goes operational now is July of this year. That was very worthwhile because it allowed a lot more time to clean up the legacy software system. And so, as I said, in July, the products will then be coming from NASA. That seems to be well on target at the moment. Starting in January of 2027, there will be work towards the multi-GNSS system. Many of you might have noticed that there is a demonstration multi-GNSS combination for finals and for ultras coming out of the current system. That is for comparison with the Wuhan Combination Center. Those two comparisons actually look extremely good. So that is being worked, and then hopefully in July of 27, there will be more enhancements to graphics and other things coming out of the NASA system. So this partnership that we've had has worked extremely well. And again, as I said, we have this transition now into multi-GNSS products. And so these works, for those, again, who have been following, the Repro 3 products were all multi-GNSS products. And the steps now have become with the IGS demo products, which was announced in IGS Mail 8682, those are now available for you to test and to play with. The orbits for the multi-GNSS is being done with the open source software from Geosciences Australia called ROCS. It's all Python based. The reference attitude model is coming from the groups software out of TU Grass. The clock and biases are being done by NRCan with the Spark Combo software. And then GFC Spock software, which also allows clock combination, is also being evaluated to give us a second view of how to combine these clocks. We've seen, again, from the BIPM presentation, how critical it is to have day boundary continuities and to have that control. So all of these, I think, are very useful works. Now, if we compare the multi-GNSS orbits to the current legacy products, the top frame is for GPS. The important line there is the yellow line at the very bottom, which says IGS, where that's yellow, which is 0 on this scale. So what it's saying is our multi-GNSS product for IGS orbits is matching the legacy IGS orbit, again, at the millimeter type level. There is differences because the weights change, etc. Then we also have examples for different groups for median, for Galileo, and for the GLONASS orbits. And again, for GLONASS, we have the MGEX product that has been generated for many years. And again, most of the time it is 0. There's one little brown spot there, which is presumably a change in, because of the JGX software, I think changed, our contribution changed between the two. So again, the comparisons look very good at this point. We can also look at the helmet transformations between these systems. And again, all of the rotations in milliarc seconds on this plot are down at less than 50, 0.05 milliarc seconds, 50 microarc seconds. Again, some issues at the beginning of the timing, and then also for Z rotation, which always is a little tricky because separating orbits from the Earth's rotation from longitudes of the stations is not a unique separation. So those are the helmet transformations between them again, and then for the orbit translations, that also works out. Very small numbers there in terms of millimeters. We also have been doing comparison of the multi-GNSS final clocks, and these are graphics that come from the Spark software, so it lets you, for each one of the centers, determine how well their clocks are matching the combinations. And again, all of these different clock values, the differences are running at the centimeter level between the clock estimates that are coming out. So the multi-GNSS rapid products, as I said, are available, and they're being made on a routine basis. There is a multi-GNSS ultra-rapid product that comes out about 20 minutes after the standard ultra at the moment. And again, this is all being done with the orbits combinations being done with the ROCS software. And again, we can compare the multi-GNSS rapid products to the regular ones. And again, the important line there is that the GPS component is remaining the same. One of the characteristics of IGS has always been that our final product is one which is robust, not necessarily the best at any time, but it is the one that is robust and has a consistent high quality combination. Oh, I thought there was one more slide. Yeah, oh, I'm sorry. Yeah, and so the final, as I said, over on the other side of the figure is again comparisons between the ultra rapid product and the orbit comparisons. So as I said, this transition is on track. We think we'll have continued very high quality products, and there will be future enhancements, and multi-GNSS is being actively developed and should be expected, and already is available for the IGS. Thank you.